Okay, welcome back to Statistical Process Control. This is Statistical Process Control 103, Measures of Variation. So we have our run charts. These are two run charts using the same data, one done by hand and one done by Excel, using these data. And it's useful using the rules of run charts to tell whether our process is in control, but we really don't have any notion about the capabilities of our process. What what observations should we expect for our operating room turnaround time, and what variables or what observations would we think are excessive, or too far from the average that we expect? So when we talk about measures of variation, we can start with a relatively simple measure of variation, and that is the range. And the range is very simply the maximum value of x sub I, minus the minimum value of x. So in this case, that would be 31 minus 19. So the range would be equal to 12. Now, that doesn't really help us. We could have a process where all the variables, all the observations are either 31 or 19, and that would give us a range of 12. And yet we could have another process where every single observation was 25, except for two, one that was 31 and one that was 19, and that would give us a range of 12. And yet the two processes would not be equivalent. So range turns out to be a pretty lousy measure of variation. So let's think a little more deeply then about how we might construct a measure of variation that would be useful for us, more useful than the range. Well, let's imagine for a minute, I'm going to get rid of this one for the time being. Let's imagine that we wanted to somehow estimate the distance, or sum the distance that each of these variables is from the measure of central tendency. And I'm just going to tell you right off the bat that we're going to stop using the median and we're going to replace it with our old friend, the mean. Otherwise known, the alias of the mean is x bar. Okay, so what is the degree to which these observations vary from the mean? Well, what if we just took all of these distances from the mean and summed them? All these distances from the mean, and we just sum them up. So we use this sigma, meaning the sum of all x sub I minus the mean, minus x bar. What would be the problem with this statistic if we were going to construct a statistic that was the sum of all these distances? Well, some of these distances are positive and some of them are negative. And since they're variations from the mean, we'd expect the sum to be pretty close to 0. So that's not really a very useful, that's going to be about 0. So this doesn't turn out to be a very useful statistic. But what if we did something to prevent this from being 0? What if we squared this value? We summed these values and squared them. Well, if we squared them, then they would all be positive, wouldn't they? So we could construct a statistic where we took, this is 30 and 31, so they are 5 and 6. This one is 25, so it was 0, and I believe this one is 20. So let's just do it for these. So for this number, so we've got, sorry, this is 5 away. So we have 5 squared plus 6 squared plus 0 squared plus negative 5 squared. So that would be 25 plus 36 plus 0 plus 25, which would be 86. Right? So that might be, if we were just looking at this, we had just 5 observations. We'd have this summary statistic of 86. Well, what if we kept going? Well, if we kept going, say we added this one, so we're now 29, that's 4, and then 21 is also 4, and then 25, then we're at 19, which is 6, and then 25, again 0. So if we add these variables, which is going to be 16, 32 plus 36 is 68. So now we have a statistic that's 4, carry the 1, 154. Well, it's the same process. Our statistic is almost doubled because we've doubled the number of entries, of data points that we've put in. So what if we compensate for the number of observations? What if we decide to put this over n, and we actually by convention make it n minus 1. So now we have a summary statistic that will compensate for the number of observations, much like the average does. Remember that the average was the sum over n. Well, now we have the sum of the squares of the differences of each of these observations over n minus 1, a number that's a lot like n. It's just n minus 1. Well, we could invent this statistic, but we'd be too late. This statistic has been invented, and it has a name, and its name is the variance. Okay, so this is the variance. The problem with the variance is it can be quite large. So, in fact, let's calculate the variance for this very set of data. Okay, so here's our table. Same 10 observations, and I've constructed an Excel spreadsheet with the mean now. I notice I've used the function for the average, again locking it down with those handy dollar signs. And now I've added this other function, which is simply doing a little algebra, subtracting the mean from the observation, from this version of x sub I, which is 30. And of course, the difference between 25 and 30 is 5. So here are all the x sub I minus x bar variables. And then in this column, we just squared them, just multiplied them by themselves. And then we summed that, and that actually doesn't give us the variance. We have to put that value over 2, over n minus 1. So let's say that this is equal to, equal to this divided by this minus 1. Okay, so that gives us a variance. And the variance is 17.3. Well, 17.3 is a big number. So how could we make a better statistic than this? Well, what if we constructed a statistic that was the square root of the variance? That would be a nice way of shrinking it down. And there's some justification for it because we squared the values here in order to get that pesky negative sign out of the way. So what if we take the square root of 17.5, 17.3, and that turns out to be 4.16. And this is a new statistic called the standard deviation. Now, in fact, the standard deviation in a sample such as this is denoted as S, but we're not going to get into the peculiarities of population versus sample statistics. We're going to call the standard deviation sigma, because that's what we do in statistical process control. We call it sigma whether it's a sample or a population. That's the last we're going to hear about that. So the standard deviation of these data, of this sample of data, turns out to be 4.16. That's an interesting number. Now, what if we change these observations? So let's change these observations so that they're much closer to 25. So let's make them 25, 26, 27, 24, 23, 25, 26, 24, 23, 27. And it turns out that our variance is quite small now, and our standard deviation is quite small. So these data, these observations of turnaround time, vary a lot less, and not surprisingly, their measure of variation has gone down quite a lot. Now, what if we put in a couple of crazy variables here? What if we put in a 31 and a 19? Well, that leaves our mean at about the same, but it increases our standard deviation appropriately. What if we change them all to 31 and 19? Okay. Okay, so here, now we've got a much more variable process that either is 19 or 31 and has the same mean, but look at this, its standard deviation, its variance is 40 and its standard deviation is now all the way up to 6. So we can see now the usefulness of the standard deviation. So let's get back to our original data set. And so here we are back with our original data set. Okay, so meet me at SPC 103B for the conclusion of this lesson. Thank you.